Hi, before going into the Raoults law, we will discuss some basic terms here. Let's create a very simple solution for just our understanding. So I have our famous glass of water and I put some sugar into it. I mix it well. So I have a solution now. So this is what the solution will be. Simple, right? So there are two things, right? Two components. So there are two components. Okay. So what I've added, remember, so I was just pouring this sugar and this was water. Right? So it is a solution of sugar and water. So there are some fancy words we should know. So one thing will be called solute and one thing will be called solvent. Okay, two components. So what is solute and what is solvent? Remember, solute will be always which is in less amount. So here we are not pouring like kgs of sugars. We are just putting 1 spoon of sugar. So that will be less quantity, less amount. So that will be called solute. What will be the solvent? You guessed it right now. That is in more quantity or which is having more amount. Right? Now we know that water and sugar are mixed together well, right? So you're not able to figure out, when we are mixing it, even we are not able to see the sugar, it dissolves completely. Or we have a word for that. These sugar and water are miscible. So fancy word again, miscible. They mix well. The sugar is getting dissolved in the water, getting dispersed in the water, right? So that is the miscible word for. The opposite of that will be immiscible. So when that will happen, let's say sand you mix, right? Hindi we call rate, sand and water mixture. So if you try to mix it, no, they'll not mix. They will not, the sand will not dissolve into the water. So it is immiscible, immiscible solution. Yeah. So these kind of fancy words, we can encounter when we are discussing. So better we know that. Now we can summarize it. The solute is getting dissolved in the solvent. So solvent is something where solute is getting dissolved. It's a medium, you can say, right? And these having two components, we will discuss only two component solution. Or there is another fancy word, binary solution we'll be using. Binary solution. So bi means here is two, right? Bi means two here. So binary solutions only we'll be talking about. So Let's discuss a solution where I have a solute of glycerol and a solvent as water. Yes, it is a binary solution. It's a liquid solution. Both are liquids. And now here I have shown it. Like on the left, you can see in the red color, I wanted to differentiate between water and glycerol. So I've used a red color for glycerol. And here we have water. And remember, both are at 25 degrees centigrade, or we can say our chill temperature, room temperature. And now for this temperature, these molecules, water molecule will have certain kinetic energy as we discussed in last video. So we will be having some vapors here and we can note down how much pressure they are exerting. Okay, how much pressure they are exerting. And if you see this part, the glycerol, it is very less volatile, less volatile. What does that mean? Let's see. So very less molecules will be coming in the vapor state. So less pressure, right? Now, why that is happening? There can be many reasons for that. So if you compare these two, this is more volatile. So volatile nature is a comparative thing, right? So if I put, gasoline like petrol, that is more volatile than water. So we can compare through that. But what does that mean? What does that mean? More volatile and less volatile, and what things can be play a role here, right? First thing is kinetic energy, what temperature they are in, how much kinetic energy they are having. The second thing can be how much strong intermolecular forces they have. So in case of this, comparatively, water to water molecule intermolecular forces and glycerol to glycerol molecular forces, intermolecular forces, they are strong. So even at this room temperature, the kinetic energy is not enough. It is not enough so that they can break and go to the vapor state. That's why we are calling them, they are less volatile. They are not readily going into the vapor state, right? So this is more volatile and this is less volatile. We are comparing. Now something for our convenience. Can I call the solute as A? So whenever I'm saying A, you got to know that I'm talking about solute. So I don't have to write solute the spellings. Yeah. And in case of solvent, I'm taking as B. So the component B is water, component A is glycerol, or solute is glycerol, and the solvent is water. Okay. So that is one thing, so that you know. Now the second thing is I wanted to note down how much vapor pressure is there, right? The equilibrium has reached. I wanted to note it down. Here also equilibrium has reached. I wanted to note down what is the vapor pressure. So let's say I calculate that. I note that, and how I can denote? I can denote for glycerol. I can denote it as PA, right? And what about this? I can denote it by PB. Yeah. And there is one, a thing, we have not mixed them yet, right? The solution we have not created yet. So they are in pure form. And for showing that pure form, can I put a round here like a degree we put? And can we put a round here, degree like that? So whatever value is there, we can say PA naught, right? That is the pressure when nothing was mixed with the glycerol. It was in pure state. What is PB naught? It is the vapor pressure of water when nothing was mixed with it. It was in pure form at 25 degrees centigrade. Now let's make a solution. So what I'm going to do here, I with these black circles, I've shown the water molecules, and I'm going to mix my glycerol. So let's say glycerol molecule, once it's here and one here. And because it is a lesser quantity, so I will show less. Let's say these three. Yeah. So this is just a representation. So now what will be the effect on evaporation? Will be there any effect on the evaporation of water molecules? So let's ask water. Oh, water molecules, what problems you are having? So he will say, focus on this layer, surface layer. That is very important, right? Surface layer. So water molecules say, now some of the space is taken by these glycerol molecules, right? So I lost the chance here. So that reason my vapors will be lesser. I'll be able to go lesser because now I have less surface available to me. So that is the first thing, right? Second, do you have any other problem, water molecule? Yes, because you have mixed glycerol with me and now they are binded with me, completely dissolved. What does that mean? Why they are stuck together now? Because they have some force of attraction. What is this force of attraction? This force of attraction is intermolecular force. Intermolecular force between water molecule and glycerol molecule. And now it will make this guys going into the vapor state difficult because now it has to, fight with this force of attraction, intermolecular force to go up. So again, two damages, right? So the water vapors which were going up in the pure form, right? Now the water vapor which we are going up will be lesser. There will be less vapor state of water due to these two reasons. First, occupying of space of surface layer by glycerol molecules. And the second thing is the intermolecular force. And due to that, this is binded now with the glycerol molecule. This is already very lazy. It does not go. It needs more energy to go into the vapor state. It is less volatile. So it is like it is going on to go up, but this guy wants to keep it back. So it has to fight this intermolecular force to go up. And the resulting reason will be there will be less vapor pressure due to water in this case, right? And if you ask the glycerol molecule, same thing, right? In the surface now, not all the glycerol molecules are there. Second thing, they want to go up. They already are very less volatile, but now they are bounded with this intermolecular force. They have to fight that. So their contribution is also getting less, right? So now the pressure which we are getting here, right? Let's say these are the water vapors and these are the reds are shown as glycerol molecules vapor state. Now this pressure which will be created, and now think about it, this is created by water molecules vapors and glycerol molecules. So everyone is playing their part, but their pressure, as we said, due to the reason stated, that will be lesser than that, right? That will be fraction of that. So now if I want to summarize it, I can say the pressure, not the complete one, but the part one, or we can say partial pressure, this will be called partial pressure by B, which is water. Partial pressure by B cannot be equal to what it was before, right? It cannot be pure. It is glycerol has taken some place. Some intermolecular phases now need to be fought, right? So that will be just some fraction multiplication of that. It may be half, 1 by 2. It can be 1 by 4, 1 by 5, right? And what will be that fraction? That will be not the volume fraction, how you have mixed them, not the mass fraction, but the molar fraction. And this, which I have written here, is called Raoults law. What it is saying is, Raoults law is saying the partial pressure, the part which this component will play in the total vapor pressure, will be proportional to the molar fraction it has. Right? So this is a constant, right? This will not change. At certain degree of centigrade, you will get the same pressure always. This is a constant. So if you play with this, if you change the molar fraction, then this partial pressure will get affected. What about solute? I forgot solute. Can you write about that? Yeah, that will be also not the complete one, right? This cannot be, it will be multiplied by some fraction. And according to Raoults law, that fraction is the molar fraction of this guy, of solute. So for both molecules, these are the part they are playing. So these are called partial pressure. So this will be the partial pressure by water. This will be the partial pressure by glycerol. And if you add them up, if you add, what will be, we'll get? We will get the total pressure, right? So we can say the total pressure will be equal to PA, partial pressure by A, plus partial pressure by another component B, solute and solvent, right? So this is what the insight, that which fraction we should multiply, how much it will be lesser than this, will be given by Raoults law. So it is giving that molar fraction. So let me write here what is this molar fraction of component B, which is water, right? And this is the molar fraction of glycerol or our solute. Now let's talk about the molar fraction because I'm using this number. So we represent it by we can say x1 and x2. What is that fraction? It is a fraction or a ratio. So let's read it: a ratio of number of moles of a particular component to the total number of moles in the solution. So simply saying, let's have a small analogy here. So like for example, you're seeing from glass from the top, okay? And let's say I can part it 4 times. So let's say I put 1 mole. This is 1 mole of glycerol. Okay, so pictorially we are understanding, and let's say these are 3 moles, 1 1 1. These are 3 moles, 3 moles of water, right? So who's the solute? Solute is glycerol because it is a lesser quantity, and here is a solvent, 3 moles of water. So if I mix them, right, what will be the molar fraction? Now molar fraction of what? So first let's calculate for this. Let's say molar fraction for glycerol, right? X A, let's say A is a solute, then I can say that will be number of moles of A, okay, divided by what is the total number of moles. Total number of moles is Na, number of moles of A, plus Nb. That is the solution. We have a binary solution, so there will be only 2 components. Can you calculate in this case? Yes, sir. The number of moles of A, that is our glycerol, is 1, right? Only one part, this one, so it will be 1. What is the total number of moles? 1 of glycerol and 3 of water. So 1 plus 3 is 4. I can write it like that, or I can say 1 by 4. So this is the mole fraction which we are going to multiply with the pure vapor pressure, and we will get the part they are playing, the partial pressure, right? So what about if I want to calculate similarly for water, like solvent? So XB, let's say. So that will be what are the number of moles of water and divided by Na plus Nb. So let me calculate. What is the number of moles of B? Oh, 1, 2, 3. Okay, 3 moles. And what is the total moles? 1 plus 3, 4, right? I can write it like that. So 3 by 4th is becoming our fraction. This is the mole fraction we are talking about. Now, if you want to know what is the part this solute is playing, what is the partial pressure of A's? So that is simply, according to Raoults law, that will be, note down from your book what is the vapor pressure in its pure form. And now it will be lesser than that, it will be partial. So we need to multiply with some fraction. And which will be that fraction? That will be molar fraction of A or solute. So that will be 1 by 4. Right? So that way we'll be able to calculate the partial pressure exerted by this or solute. What about PB? Note down what is in its pure form, what's the vapor pressure. We'll reduce it by multiplying it with some fraction, but that fraction will be this fraction now, the solvent's mole fraction, and that will be multiplied by 3 by 4. So that's how we are thinking about Raoults law, how it helps us to calculate the partial pressures which different components contribute in the total pressure.